A2 Further Maths, t-distribution. Right, before we go into t-distribution, what I'd like you to do, please, is just practice some of your normal distribution skills by running the hypothesis test on this situation. So I'll give you an opportunity to read it and see if you can investigate to a 10% level of significance whether the mean length of the bars has decreased or not. Okay, so just have a read of it, pause there until you've done it, and then we'll check through your answer. Okay, so we need to, before we move on to t-distribution, we need to make sure that you fully understand how to run hypothesis tests with normal distribution. So what you should have found is this factory produces the metal bars with a length of 1 metre. As you can see, most of the sample there is roughly 1 metre. They introduce a new bar and there's a suspicion that the length of the bar has decreased. So they think the bar has decreased. You've got a random sample of 12 bars taken. There we go. And what's important is the length of the bars is normally distributed. That bit is vital. It has to be normally distributed for us to be able to run this normal distribution. And also that the sample deviation is given to you as 0.5. Okay, so you've got both of those bits of information. So I want you to investigate to a 10% level. Right, so the first thing we want to do is just run through each of the steps, almost like an algorithm on how to run a hypothesis test. So I'm going to define the population parameter. So I know that mu is my mean length of a metal bar in centimetres, because the lengths are in centimetres. So that's my mean length, mu. I'm going to state the null hypothesis and the alternative hypothesis. Now the null hypothesis is the no change. So they expected it to be 1 metre in length. The machine's trying to get 1 metre in length. So my mu value is set to 100 because that's the length of the metal bars in centimetres. My alternative hypothesis is you have to read the question, find a bit of information that's important. After the introduction of a new machine, there is suspicion the mean length of the bar has decreased. So my alternative hypothesis is that the mu value is actually less than 100. We think it's decreased. What's the significance level? There we go, 10. Let's just make sure that we're aware in case we have to half it if it was a two-tailed test. So in this case, it's not. It's one-tailed because we're looking for just 100. So we're looking for the 10% mark. Okay, so once we've done that, calculate the sample mean and the test statistic. So this is a normal distribution. You're given the sample mean in your formula book, and you're given the sample mean in the question and how to calculate the test statistic in your formula book. So we've got our mean of 99.85. All right, so once I've calculated that, hopefully you do that yourselves, add them all together, divide by 12, gets us a mean of 99.85. The test statistic is worked out using this formula. So we've got our sample mean, take away the parent mean, which is 1 metre, divided by the standard deviation over the root of the sample size. So if I type that in my calculator, I would get that bit of information, 0.5 being the standard deviation, 12 being the sample size, equals minus 1.039. Now what I need to check is whether at 10% level, 1.039 takes you over that critical value. So that's what I'm going to be checking now. So I'll keep my test statistic on there. And the next thing I need to do is calculate the Z-score using that significance level. So I've got my calculator I can do that with. So I'm looking for, because it's a Z-score, that means the mean is 0. The standard deviation is 1. So I can type that in my calculator, type in 0.1, what's the probability of 0.1, and your calculator will tell you the answer for the Z-score is minus 1.282. This had to get as far down as minus 1.282 for me to reject the null hypothesis. Now, as you can see, it's not quite there. So in this case, there is our critical value at the bottom 10%. We're looking to see whether we cross that critical line. Now in this case, as we can see, 1.039 is not past that critical value. It's within what we call the acceptance region. So therefore we accept the null hypothesis. All right, to a 10% level of significance, I would accept that null hypothesis. So there is sufficient evidence to suggest, not to confirm, it's not definite, but it suggests that the mean length of the bars has not decreased from 1 meter. So even with the new introduction of the new machine, I would still say that there is sufficient evidence to suggest that the machine is still producing metal bars of 1 meter long on average. Okay, so same machine, we're just doing something slightly differently. All right, this is from your first year further maths. So what I'd like you to do, please, take the information, still got the same sample, we've still got the same standard deviation, so that saves you a little bit of legwork. And what I'd like you to do is construct a 90% confidence interval for that, please. Okay, so pause it there, make use of your notes, see whether you can construct a 90% confidence interval for the mean length of the metal bars. Okay, so just a reminder then, a confidence interval is two numbers and you are 90% confident that the actual parent mean lies between those two numbers. That's what we're going to find out now. So we're going to calculate the z-score for 90% confidence. All right, now to do that, that means that the middle section of the normal distribution curve. So you think about the normal distribution curve, the middle 90% would leave 5% at each side. So you could think of it a bit like this. There's your normal distribution curve. There's your middle 90%, just there. So we think about that as our middle 90%. And then that means that these two values just here are going to be 5% each. Now, because that's 5% just there, I want to find this value just here. This is the important value. Now look, if you're looking for that value, you're looking for less than that value. So it's 90 plus the 5. So to use your calculator going to do less than. So you're looking at the 90%, which is what we've got a confidence interval, plus this tail here, which is worth 5%. Okay, which is why we're talking about find the value for 95%. Okay, so type that in your calculator. And what we're going to get is a z-score of 1.645. So below 1.645 is going to be our 95% value. Right, define the sample mean and the standard error. So we need to figure out what the sample mean is and the standard error. So the sample mean was 99.85, which we discussed before. The standard error is the bit that was underneath the square, underneath the previous part, the denominator of the previous part, the sigma over root n. So that's 0.5 over root 12. Once I've got that, that's going to give me a standard error of 0.144. That's what we can use as a standard deviation of this sample just here. Okay, 0.144. Right, so the formula looks like this for a confidence interval. It's going to be your sample mean minus whatever your z-score is. In our case, it's 1.645 times by standard error. And the other side is going to be plus z times the standard error. So it's just the mean plus and minus these two parts just here. Now in this case, we could type the numbers in and we know that is a 90% confidence interval. And what you would say is you are 90% confident that the parent mean of that sample is somewhere between 99.6 centimeters and 1 meter 0.1 centimeters. So somewhere in between those two values. Okay, right, so you practiced doing hypothesis tests with normal distribution, and you also practiced doing confidence intervals with normal distribution. Nothing new, both of those you've covered before in both maths and further maths. What we want to do is look at a slightly different situation. Okay, so let's have a think about this situation. Factory produces the metal bars, so the same factory we were just talking about. And let's just take one sample. You pick it up, and the metal bar is 99.5 centimeters. Now, would you doubt the claim that the mean length is 1 meter because that one sample of 99.5? Okay, if you said no, you wouldn't doubt it. It's not enough information or not big enough sample or anything like that. I would agree. All right, it's not enough, is there? What about this though? You pick up one metal bar, just one metal bar, and it's 95 instead of the 99.5. So one sample, which is still not big enough, but would you doubt it if it was 95? Would you now be thinking, 95, that's a lot smaller than a metre, so therefore now I doubt the claim? And what about if it was 50 centimetres? Would you doubt the claim? Now the truth is, you can't doubt the claim at all for either of those two things. And the reason why you can't doubt the claim is because you don't know what the standard deviation is. Without knowing the standard deviation, how do you know that the machine doesn't produce bars, between 90 centimetres and a metre 10? Maybe it's a factory that doesn't need to be so accurate with its metre bars. It's still a metre long on average, but you can get bars from anywhere between 90 and 110 centimetres, in which case 95 is fine. If it's a machine that has to be super accurate, so your standard deviation is very tight, in other words, you mostly get bars between, let's say, 99.9 and 1 metre.1, then yes, you would certainly doubt both of those, that the machine is working properly. So without knowing the standard deviation means that you can't make judgments on these values at all. And that's what we're going to look at now. Every question you've done so far has always given you the standard deviation. It's always given you the standard deviation. And so therefore, certainly the questions you'll be doing have been quite small samples, you've always given that standard deviation. And that means that you could go on and answer the questions to do with hypothesis tests and confidence intervals without any problem at all. Now, what we're going to look at is situations where you don't know the standard deviation. Okay, so what I'd like you to do is, just thinking about standard deviation for a minute, I'd like you to pick any 12 of those numbers, any 12 you like, stick them in your calculator and see if you can work out the standard deviation for me. Any 12 you like, just pick them randomly, just pick a row or a column if you want to. Read off the 12 numbers, stick them in your calculator and see if you can work out what the standard deviation is. Okay, so pause there until you've done that. Okay, so I'm going to just pick 12 at random. Dun, 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 dun. Okay, so I'm picking my 12 values. And once I've picked my 12 values at random, I'm going to work out the standard deviation for that sample. And the standard deviation, I can use the formula, or you could just type in your calculator, which I'm sure you all did. The formula looks like that. Okay, the difference between the sample and the mean. So you have to calculate the mean, square each of them, divide it by n minus 1. So on your calculators, if you use the SN button as opposed to the SN minus 1, it's not going to make a big difference at the moment, but it might be worth going back and just checking what the other standard deviation. I'll talk about the difference in a second. So the SN minus 1 button to work out your standard deviation. Now, if I did that, I've got 4.899. So I could then go on and use that 4.899 as my standard deviation. The problem is the actual standard deviation of that entire parent population, all of those numbers, is actually closer to 5.14. So what's going to happen is my standard deviation is going to be different to the actual parent standard deviation. And you're going to make judgments about the mean when your standard deviation is actually different. And so for this, what we're going to have to look at doing is using what we call student's t distribution, which is a slight variation on the normal distribution, but it takes into account the fact that your standard deviation is slightly off, slightly different. Okay, just a minute ago I said to you using the standard deviation button on your calculator, and I said you want to pick n minus 1. You pick n minus 1 if you've taken a sample. If you were collecting all of this data, this entire set on the screen here is what's called the parent population. Now, if you worked out the standard deviation of all of that, in other words, you typed every single one of those numbers in, then because it's everything, you would divide it by n. Any sample, doesn't matter how big or how small that sample is, then you need to divide by n minus 1. Now, you'll notice the bigger the sample, the less difference this makes. You imagine dividing by 1,000 or dividing by 999. It's not that much difference. If you're dividing by 10 or dividing by 9, that's a bigger difference. Okay, so this bit here is important. It's always what you divide by n minus 1 if it's a sample. Okay, question is, how could I improve that estimation? So it's not far off, it's not brilliant, but I could improve it. How could I do that? How could I improve that to get it close to that? Okay, this same answer comes up for a lot of things. How would you look to improve it? You take a bigger sample. The bigger your sample you take, the better that approximation will be of that. Okay, very, very close if you get close to about 30 pieces of data. And that's what it says there. If you take a sample of about 30 pieces of data, these two numbers are generally accepted as being close enough for you to use normal distribution. So the questions you may have done so far, you might not have known about the standard deviation, but it didn't matter because your sample would have been big enough. So if you want to use normal distribution, you must make sure that your sample is bigger than 30 unless you already know what the standard deviation is. If you know what the standard deviation is, it doesn't matter about the size of the sample as long as the data is normally distributed. If your sample is bigger than 30, if your sample is bigger than 30, you can accept the standard deviation as being pretty much the same as the parent. All right, pretty much the same. And it also doesn't matter what the distribution is either when you take samples of 30. Right, so grab your notebooks then, please. What we want to do is we want to just have a look at when we should use normal distribution and when we should use t-distribution. So if you're given a normally distributed population with an unknown standard deviation, that's the important bit. If it's a known standard deviation, then you just use normal distribution on your calculator, no problem. If it's unknown though, you might have to use students' t-distribution. If your sample is small, and by the word small there, I would put less than 30. All right, so if your sample is small, then you should use t-distribution rather than normal distribution. So if it's unknown standard deviation and a small sample, anywhere between 1 to 30, then we'll use t-distribution. Over 30, let's say you had 100 pieces of data or 1,000 pieces of data, then yes, then you can use normal distribution. Now, t-distribution and normal distribution are very, very similar. So I'll show you what I mean. There's normal distribution. Okay. Now, t-distribution looks like that. Look at the difference. It's lower in the middle and it's sort of wider on each end. It's a bit more spread out to account for the fact that your data isn't as tight around the mean. Okay, it's more spread out. So things like my confidence intervals would be bigger. My critical values would be bigger for hypothesis testing. But you can improve t-distribution and watch what happens to the graph as we look at increasing the size. So the bigger the size of your sample, the closer and closer that t-distribution approaches till it gets to normal distribution. So t-distribution for small samples is a good approximation, right? Good approximation, but the bigger your sample, the closer and closer it gets. And the moment you get to about 30, you can stop using t-distribution altogether, and then you can use normal distribution. All right, so if your sample gets bigger than 30, you don't need to worry about t-distribution at all. You can just use your normal distribution. Okay, so this says notebook, but obviously you can't copy these bits into your notebook. What you can do is you can grab your formula book and make sure you've seen this in your formula book. So just pause there, get your formula book out and have a look for this table 1. Your t-distributions are in that formula book. You can also use the table at the back of the textbook. Okay, so you're looking for the t-distribution part, students' t-distribution. Okay, that's because your calculators, they can do normal distribution, but they don't do t-distribution. So you're going to have to learn how to use the tables for this. Now the tables look like this. This is your critical values. Now normally, like we saw at the start of the lesson when we did that normal distribution question, the calculator tells you what these critical values are. Okay, your calculator will work them out for you. But it doesn't work out t-distribution. So what we need to do is we need to figure out how to do this. So just some of the bits for your notebook. The critical values can be found on the tables if sample size n. So whatever your sample size. This is the important bit though. This is the bit you need to put down in your notebook. The number of degrees of freedom is always one less than the sample size. Okay, exactly the same as what we saw in chi-squared. Same sort of idea with this. That's because one of the values is fixed. So therefore it's the degrees of freedom are all but one of the values. So look for whatever your sample size is, take away 1 down this side of the table. So say for example I had a sample of 10. I don't look at 10, I look at 9. I look at 1 less than my sample size. So that would be my new value. The critical values go along the top. So you can find your critical values along the top. And again, they work out those sort of standard values, 90%, 95%. 97.5 doesn't seem like standard, but that's because you might be doing a two-tailed test for that, or a confidence intervals for 95. So 97.5 fits with that one. 99, and of course 99.5 fits with that value. Okay, so you've got all the standard confidence intervals at the top. Sorry, all the standard critical values. The sample size, you'll notice that to start with, these numbers change massively. Look at that. If you had just a sample of 2, 2 minus 1 is 1, right? You have to have a sample size of at least 2. Then you look at these values here. The critical values are massive. Look at that, 12, 31. All right, so having a sample of 2 doesn't really help. You have to be really, really sort of ridiculously close for it to be accepted, because 63 is what you're multiplying by if you're thinking about either side of a confidence interval. All right, or 63 is what you're looking for if you actually do your hypothesis test. But look, the moment you start stepping up and you say, right, my sample size is 3, so that's a new value of 2, look at the values, they decrease rapidly to get to those. If you've got a situation where you've got a sample of 10, look at 9, there we go. These values are starting to become very, very similar. Now, if you get close to 30 and then to 100, 125, a sample size of 200, then these values are so close to normal distribution, we just don't use t-distribution anymore. And in fact, at 30, it's a bit acceptable. You'll notice here, it's got infinity. That means that's what your normal distribution is. So for 95%, you type in your calculator, 95% confidence interval, then you'll notice 95% for your critical value, your probability, then you will get 1.645 coming out as that critical value. Okay. So if we had a sample, just mention this, 11 degrees of freedom, then we can see a probability of 95% would get me a critical value of 1.796. I don't need to use my calculators for it, but if you try doing a 95% probability in your calculator, you'll notice it comes out to be 1.645. They're very similar, but it makes sense that the t-distribution is slightly bigger. So it means you're going to have a bigger confidence interval. It's more spread out. Okay, probably a further away critical value when it comes to your hypothesis test. So you're going to less likely to accept it, or sorry, reject it. It would be. In this case, yes, the critical value is 1.796. Okay, so test for the mean and the normal distribution with an unknown standard deviation and a small sample. So both of those are alarm bells for you to realise you need to use students' t-distribution. You will be expected to spot it. You will not be told. You're looking for 3 key facts. Is the data normally distributed? Yes. Do we know the standard deviation? No. Is the sample big enough so that we don't need to know the standard deviation? No, it's a small sample. These are the 3 important facts that tell you to use t-distribution. If any of these were different, you would use normal distribution. Big sample, normal distribution. Known standard deviation, normal distribution. Normally distributed has to be accepted as well, unless the sample's big enough. Okay, so then we're going to go through and we're just going to do a hypothesis test for this then. So we know, the first thing we need to do is define the population parameter, same as before. Then what I can do is I can state the null and the alternative hypothesis. Right, same as what you would do normally. There's no difference between these two to what you did at the start of the lesson. we're going to calculate an unbiased estimation of the mean and standard deviation. Now this is the bit that is different. Usually you just do the mean, but in this case, because we don't know what the standard deviation is either, we're going to use our sample to calculate the standard deviation. So this is what we call our standard deviation. S equals this formula, or you could write this formula. They both do the same job, but you might be given that as a value you know. You might be given these bits as values you know. We'll look at an example of that in a second. So once you've calculated your standard deviation and your mean, then what you can do is you can calculate the test statistic the same as before. But look at the difference. Last time that was sigma. This time it's S, because it's our sample standard deviation we're substituting in there. So it's going to be slightly different. But this time as well, because you are using t-distribution, the critical value is not Z. It's not a Z score, it's going to be a T score. So you can work it out from the t-distribution. Just be aware that your new value is always the sample size, whatever that sample is, minus 1. Once you've done that, you can compare the two and make your conclusion. But have a look, it looks exactly the same as what you did at the start of the lesson for normal distribution, except you have to calculate the standard deviation yourself and you use t-distribution instead of normal distribution. Okay, so what we're going to do is just look at an example then. So we've got 14 apples selected from Bill's fruit shop. Give you a chance to read the rest yourselves and maybe have a go yourselves if you want to, or just pause there, write it down and then wait for me to go through the answer. It's your choice. Okay, so let's have a look. First thing sort of is a bit of alarm bells is the fact that it's a small sample, only 14 apples, well below that 30 mark. Selected at random. The sample of apples has a mean weight of 97.3, so they're giving us the mean, we don't need to calculate it ourselves. And the standard deviation of the sample, S, is 25.2. So we don't need to do any work. They're giving us the mean and the standard deviation of the sample. I've also noticed the distribution is normal. So there's nothing wrong with me solving this question as I would do normally with the normal distribution, but I need to be aware that I am using a sample. So therefore I should be using t-distribution. All right, there's nothing given about the parent standard deviation. That's the key word you're looking for. Right, so I'm going to test that the mean weight of the apples is 110 using 10% significance. So define the population parameter first of all. Well, my mu value is the mean weight of an apple. All right, see that there, the mean weight of the apple. My parent, the null and alternative hypothesis are given to me as the mean of 110, and I'm just looking for what's the probability it's changed. We're checking that claim. We don't know whether it's right, we don't know whether it's bigger than that or smaller than that, so therefore our mu value is going to be not equal to 110. We're just checking that claim. The alpha value is 10%, but don't forget, because it's a two-tailed test, we are looking at halving that to get 5%. So it's important to make sure that you're thinking about what the probability is going to be from your significance level. Okay, once I've done that, calculate the unbiased estimation of the mean and the standard deviation. Now both of those are given to us in this question. It's more likely sometimes you have to calculate those two bits yourself. And this bit that says unbiased, what that means is you divide it by n-1 to get an unbiased estimation of the standard deviation. The mean, you don't need to worry about that. It's always an unbiased estimation of the mean. Okay, but if you divided the standard deviation by n, you would get a biased estimator. Okay, so it's important to think about that if you have to work out the standard deviation yourself. Calculate the test statistics. So that's you grabbing the formula and noticing that instead of using sigma, you're using S. Apart from that, it's exactly the same. It's the same formula. All right, your sample mean, take away the parent mean, divided by your standard deviation, divided by root n. All right, no difference at all. You're still putting in 14 in for n, and the rest of it you just number crunch. So there's my point. What I need to do now is figure out whether that passes the critical value or not. Okay, so let's figure out if we've got the critical value or not. So we're going for the t-distribution table because I've recognised that it's not normally distributed. And once I've gone to my t-distribution table, I know I'm going to be using a new value of 13. So make a nice note of that. 14 apples, n minus 1 gets me my new value of 13. So then I can find that on the table. And then once I've found it on the table for 13, for the new value of 13, I can then figure out which percentage I'm looking for. Now it was 10%. Just be careful not to use 0.9 though, because it is a two-tailed test. So therefore it's 5% on each end, a bit like a confidence interval. You're using 0.95. So I'm looking for that value. And there we go. Where they cross is my critical value. Notice that this table only deals on the positive side of the curve. All right, on the bell-shaped symmetrical curve. And that's because if you're looking for the opposite side, you could just take the negative version of that. So in this case, my t score, my t value that's important is minus 1.771. It's a negative version. And now I can just compare and write my conclusion. So does that get me past that point? Well, if I'm thinking of a number line going backwards, minus 1.7 there, minus 1.886 there. So definitely that is smaller than that one. It's past that point. So I would say we could reject this hypothesis just here, that the mean weight was 110, and you write something along those lines. There is sufficient evidence to suggest the mean weight of the apple is not 110. Okay, pause there if you need more time. All right, so have a go at these exercises on page 101 then. Have a go at just practicing using the t distribution. Okay, so what we're going to do is look at how to use it with confidence intervals. So a population is normally distributed. That's good, that's important. And has an unknown variance or an unknown standard deviation. Both of those are important. The sample size is small. Right, then what you should use to work out your confidence interval is this formula just here. And the same as before, look, it's almost identical to the one that you used to use in year one, except you're using t-score instead of a z-score, and s for your standard deviation as opposed to sigma. Apart from that, it is almost identical. Right, almost identical. Okay, so just put down what these values are for your notes. T is your t-score. Don't forget your new value is n minus 1. S is your unbiased estimation standard deviation. It has to be unbiased. We'll talk about that in a second when we look at some examples. And n is the size of the sample, where n is less than 30. Because if n was bigger than 30, the sample was big enough to use normal distribution. So we're only talking about small samples. That's when t-distribution comes into play. Okay, pause there. Take down what you need. Okay, so I'll give you a chance to write this question down in your notebook and see if you can figure it out yourself. Okay, so let's have a look and see how far you got. So the volume of the standard glass is assumed to be normally distributed. Good, we know it's normally distributed. That's the first tick box sorted. A sample of 12 glasses, right, small sample. That's the second tick box. So we've got that. Not mentioned what the standard deviation of a standard glass is. Therefore, that's the third tick box ticked. So I have to use students' t distribution. Normal, small sample, no standard deviation given. Going to be t distribution. Right, so what I can do now is, now that I understand it's t distribution, I still find a 95% confidence interval, same as what I would do normally. So I need to think, if I've got the mean and the standard deviation, the unbiased estimation standard deviation. Okay, now you can grab your calculator at this point, put all those in your calculator. Your calculator can work out the mean and the standard deviation. Just make sure there's the mean of that one and your S score was 2.065. Okay, so if you're looking at the two values, you're picking the bigger out of the two. Always a bigger one. Okay, because there's two standard deviations. Your answer should, if you have to choose between the two, look at them both and always pick the bigger one. That's the unbiased. The biased estimation is the one that's smaller because you're dividing by 12 rather than 11. Okay, so I've managed to work out my mean and my standard deviation from that sample, just using my calculator. And now what I can do is I can get the formula and I can work out the t-score and I can put it all together. So my t-score for a 95% confidence interval, be careful, 95% confidence, as we drew a minute ago, means that there will be 5% between the two sides. One of them is going to be 2.5, so therefore add the 2.5, add half the tail to this, and that will help you work out the value. So in this case, 95% is 97.5. 95% in the middle, 5% on each side is going to be 2.5 on each side. 95 plus 2.5, 97.5. New value, 11. All right, 11 degrees of freedom because there's 12 glasses. So you can get your formula book. There's my knee value of 11. There's 97.5. So I would say 2.201 is my t-score. So I've pretty much got most of the information now. I think I can go away and do the formula. So my formula looks like this. Mean, that value there, take away some amount of the standard error there, plus some amount of the standard error on this side. And what it would form is, when we put number crunch it, that value just there. You are 95% confident that the parent mean lies between 256.3 and 258.9, whatever it is, milliliters. Okay, you are 95% confident, all based on just that small sample of 12 glasses. Okay, do not forget to write down the last bit of blurb. That's necessary. Pause there and we'll look at another example. Okay, so last example then, before you can have a go yourself. Just want to show you an example of where they don't give you the data, but they do give you the sum of certain parts of the data. So, height of male staff in an office, normal distributed. There's your two sigma bits, sum of all the x's, sum of all the x squareds, and you want to construct a 99% confidence interval. Again, get yourself a chance to put it down in your notebook, pause, have a go yourselves. Okay, so hopefully you picked t-distribution. You can see why. They're normally distributed, good, that's essential. Small sample, 8. No mention of the parent standard deviation. Okay, nothing's mentioned about the standard deviation given to you. So therefore it's going to be t-distribution. Right, so I need to work out my mean and my standard deviation. Now, because I'm not given all 8 pieces of data, I'm just given the totals, I can still work out the mean, because the mean is add up all the x's, sum of x, divided by n. So I could definitely work out the mean, because it's going to be 14.2 divided by 8. This value just here, I'm going to have to use the formula. So the formula is sigma squared over n minus the mean squared. So it's 25.4 divided by 8 minus the mean squared. Now that on its own, this section on its own, all right, the mean squared minus, sorry, the sum of x squared minus the mean squared is going to get you what we call a biased variance. It's going to get you a biased variance. So what you need to do is multiply it by n over n minus 1. So check back in your notes to a couple of pages ago. You'll see that's what we wrote down, and it's worth making sure that you're well aware how to change from a biased standard deviation to an unbiased. Now, I said standard deviation, I meant variance. I apologise. Okay, because it's not be square rooted. So we can work out the biased variance and change to the unbiased variance. We can then square root, of course, to get the standard deviation. So this variance is that, and that implies that the standard deviation then is 0.1669. So there's my standard deviation. Once I've got S, I've got X bar. What else do I need? I've got N is 8. I need my t-score. So I can get my t-score, 99% confidence interval. So that would leave 1% each side. Half of that is going to be half of percent. So I'm looking for when 99.5. A knee value of 7, because we've got 8 staff members. So grab your formula book, knee value of 7, 99.5. There we go, 3.499. Quite a big score there. All right, which is likely because you want to be 99% confident. So the higher the confidence, the bigger the spread. You look at this. So when we put it in, we put the t-score, we put the date, we put the standard deviation, we put everything in, and I am 99% confident that the mean is between 1.57 and 1.98. All right, so you're really, really confident, but your range is massive. So you've got to pick between when is that high enough confidence. There's no good being 50% confident, but would 90% confident work in this case? Yeah, probably 90% confident, and you'll get a tighter gap just there. Okay, so those two always go hand in hand. The bigger the confidence, the bigger the gap in your confidence interval. Okay. Right, just pause if you need more time to write anything down. Okay, so just to finish off then, have a go at exercise 6B on page 123, and that is all your statistics now covered.